Well, I mean, all I can say is wow. I mean, gee. I've traveled all over the world and done conferences all over the place. This is my first time in Russia, and I don't think I've ever received as warm a reception as you people have given me. The signings, the photographs, the shaking my hands, the thanking me for writing the books and everything, wow. Had I known, I would have been here a lot sooner, and maybe I should move here now, I don't know. I have to talk to my, well, thanks. So it's very nice to meet all of you. And as you said, I'm very happy to sign books, I'm very happy to take photos, I'm very happy to have conversations with you. And so we set up this table after this session here, and maybe we'll do it again tomorrow or something. But I'm around like most of today, if not all today, and tomorrow. I fly back to the States on Saturday. So there should be plenty of time if you want to spend a couple minutes with me or something to find that time. And I'm happy to do it, as I said. So, okay, so without any further ado, let's start our topic, which is generics. A little introduction to me. So I'm Jeff Richter. It seems like a lot of you know that already. I now work at Microsoft. I joined the company as a full-time employee about 3.5 years ago, and I'm a software architect on the Azure team. Most of you seem to know me from the books that I've written. I put some of the books here. Those are, of course, the English versions of the book. And a lot of times people ask, will I be doing another book? I don't think I'll revise the Windows via C++ book again, although my co-author, Christoph, is right here in the front row, so you could talk to him too. We worked on the 5th edition together, and we've maintained a friendship over these years. I might revise the .NET book for .NET Core. Right now I'm not working on it, and I don't know for sure. But what I have done recently, though, about a year ago, is my new book is not a book, but instead it's a video series, a 6.5-hour video series. It's 53 videos on how to architect distributed cloud applications. And it's free, there's no charge for it, and it's available on YouTube here at this link. And if you are building distributed cloud applications, I'd highly encourage you to look at it. It's technology agnostic, so it's not about Azure in any way, or Amazon, or any of the other competitors. It's just about what are all these different terms that we have, like what's a container, and what is a load balancer, and when you have data, how many replicas should you have, and how should you partition it? And it tries to put all of these things together into a cohesive story to explain how they all relate to each other. So hopefully you would find that valuable. At the bottom of the slide is my email address, my LinkedIn address, which I learned recently. LinkedIn does not work here in Russia. So good luck with that. But you know, if you have a VPN or something, you can, I'm sure you can make it work. And then my Twitter handle all the way at the bottom. All right, so that's it for me. So now we'll get into the core content. So the way I like to think about generics is that it's another form of code reuse. With object-oriented programming, and .NET is, of course, an object-oriented programming language system, you have a form of code reuse in the form of inheritance, where one developer creates a base class, and then another developer derives off of that base class, and they've basically inherited the implementation of the base class. So they're reusing that code to make the person who's writing the derived class, their job is easier now, because they don't have to write everything all from scratch. With generics, it's another form, and a very different form, of code reuse. And it's just as valid and a useful thing to have. So the canonical example is a list of T. It's very common for people to work with collection classes, like a list that's dynamically growable and shrinkable of a set of objects. But those objects, you might want them to be of a certain data type. So some developer goes and defines this list algorithm that knows how to maintain a collection of objects, but the data type is going to be determined by the person who's consuming or reusing that algorithm. So here I show a list class that some developer has created, and it's T stands for a data type. It's effectively a variable. And when somebody creates an instance of this, there will be a field in it called elements, which is a single dimension array of T. This variable T will be replaced by the data type that you want to use at compile time. The add method here takes a T, where you can pass an element to add it into the collection. There's an indexer property here that can go and get or set a value of type T at a certain index within the collection. And then there's a count property here, just returns the number. So this is the code that is defining the generic algorithm. And then on the bottom right here, I show code that wants to reference or reuse that algorithm. In this example, the developer wants to use that list algorithm, and they want it to be a collection of date-time objects. So they are specifying a type, date-time, for this variable t. And the moment they do this, it's as if all the t's in this algorithm here have been replaced by date-time. So now we get a bunch of benefits from doing this. The add method here now takes a date-time. So you can, of course, pass it a date-time. And if you were around in the .NET 1.0 days, which I was about 16 years ago, we didn't have generics at that time. So the closest thing we had to what I'm showing here is the ArrayList class, which still ships with .NET for backwards compatibility. And the ArrayList class had an add method that took object, which is the base class of everything. So you could end up having a heterogeneous collection. So if I created an array list, I could put date times in it, or I could put integers into it, or I could put strings into it. And there was no way to enforce, at compile time at least, there was no way to enforce a homogeneous collection where everything was of the same type. But with generics, we can specify a type which makes it, or does give you compile time enforcement of a homogeneous collection. And furthermore, in the old way, where ArrayList add method took an object, if you passed in a value type like date-time, then the compiler had to box it first. And boxing is a very expensive operation in .NET. It causes memory allocations to occur, and it causes memory to be copied into the heap, and then eventually those objects will have to be garbage collected later on. But with generics, because this method now truly takes a date-time, which is a value type, this can now be passed by value, and no boxing occurs. So not only are we getting better compile time, type safety, but we're also getting much greater efficiency in our code base. We're creating fewer objects. That means less garbage collections. That means things run faster. So there's a ton of benefits that come out of using generics. In this second example here, I'm passing in another date time, which again would mean that there's no boxing because it's just passed by value into the method. And here I'm trying to call the add method and passing in a string. And if this were an array list, this would work. But because this is the generic list type, this now gives a compile time error because you cannot pass a string to a method that wants a date time. And so this is where we're getting that compile time enforcement of type safety. Also, when we go to the indexer property here at the bottom, and I'm pulling out element 0 from the collection, this is now returning something of type T. And because T is a date time, I'm pulling out a date time and putting it into a variable of date time. And so there's no casting, and it is a field copy operation, so there's a slight perf hit there, but that's it. If this was an array list instead, the indexer property returns something of type object. And you can't put something of type object into a date time. You would have to cast it. So your code, you'd have to insert the cast operator there in parentheses. And not only does that make your code uglier by doing that, but that has to be enforced at runtime. So at execution time, the runtime engine has to make sure that what you're pulling out of the collection is truly a date time, and there's a runtime hit involved in doing that, or a performance hit involved. And of course, if it isn't, then it would throw an invalid cast exception, and if it is, then the copy would be successful. In this case, with generics, the compiler and the runtime know for a fact up front that this is a date time, and therefore the cast is not required, and it can simply copy. So we get cleaner looking code, and we get more efficiency. So as you can see, there's just a ton of benefits that come up with using generics. A lot of that I've already said here on this slide. I've mentioned the type safety at the bottom. I've already mentioned the performance improvements that we get. And at the top of the slide, I've also already mentioned about the algorithm reuse, and that's really the benefit. One developer gets to create this generic algorithm, and another developer gets to specify what data types the algorithm operates on. Okay, so now, what's allowed to be generic? There are 5 things that are allowed to be generic, and those are classes, structs, interfaces, delegates, and methods. And I give examples of those all at the bottom of the slide. Here's an example of a generic class called node of t. This is an example of an object that could be a node in a linked list, where each node of the linked list has a piece of data in it, which is of type t. So it can be a linked list of date times, or a linked list of strings, or a linked list of integers, whatever you like. And then there's a next field in here, which points to the next node of t. Down below it, I show a struct example. This could be a structure in, let's say, a key-value pair collection, where you have a key along with its associated value. And here's a structure called pair, and it takes 2 generic parameters, t-key and t-value. By the way, this convention of using t in front of something, it was me who came up with that, actually. And it came from the I comparable, right? So we have this convention of putting I in front of interface names, and when we were working on generics back in the, I don't know, 2004 or so time frame, because I was on the .NET team at that time working on this with them, then everybody was using K and V for key and value, but you couldn't tell in your algorithms whether they were types or not. And then it was me who said, why don't we put a T in front to represent type, just like we put an I in front of interfaces? And so that took off. How about that? So anyway, so we have a pair that has a T key and a T value, and then, of course, there's just 2 fields in here. One is the type of the key, the other is the type of the value. Then we have the interface definition, I comparable of T. It has a compare to method that takes a T. We have delegates or callbacks. This is an action of T. That takes in a T and returns void as an example of a delegate. And then an individual method can also be generic too. And here's an example swap of T that takes 2 items by reference. They're both of the same type, T. And then we have a local variable or temporary variable, temp, also of type T. And then it does the swapping algorithm. So those are the 5 things that are allowed to be generic. Now, when it comes to methods and methods only, then there's this special feature that the compiler provides, which is called generic method type inference. And this is a syntactical convenience to you where the compiler will look at the parameters to a method, and based on what you're passing, the types of the variables that you're passing for parameters, it can try to infer what the data type T is supposed to be. And as I say, this is a syntactical convenience. It means that you can type less code into your editor when you're writing your code. So here's an example of it, where I have 2 Booleans, B1 and B2. To say that they're both Boolean data types, and one's initialized to false and the other's initialized to true, but their values doesn't matter at compile time. The only thing that matters at compile time is the variable's data type. So these 2 variables, B1 and B2, they're Booleans. What their values are doesn't matter. And if I want to call that swap method I showed you on the previous slide, then the proper or the official way to do it is to give the name of the method, pass what data type you want, right? So I want to reuse the swap algorithm with my data type called Boolean, and then you can pass in your 2 Booleans by reference here, and because the line is completely compile time type safe, the compiler will compile the code and will execute the code and everything works just great. However, as a syntactical convenience, you can leave off the angle brackets and Boolean here, and the compiler will say, well, I see you're passing a Boolean here and a Boolean here, and so you must mean that you want T to be a Boolean. So these 2 lines of code are actually identical. They compile into the exact same thing. They have the same runtime performance, the same runtime memory overhead. It's simply a syntactical convenience to you to leave off the angle brackets. And here's another example where I have 2 variables, S1 and S2, and they're both of type stream. And again, one's going to be a file stream and the other one's going to refer to a memory stream, but that doesn't matter, right? Because this is only done at compile time, it's not done at runtime. And here I'm calling the same swap method I showed before. Again, I'm leaving off the angle bracket. Stream is what you would have to pass here. But I'm passing in S1 and S2. And the compiler says, well, I know they're both streams, so you must want to swap streams. Right? And again, it's just a simple syntactical convenience. And you only get this syntactical convenience for methods. You don't get it for any of the other 4 things that can be generic, which are all data types. Now, the most common place where we as software developers use generics is working with collection classes, and many collection classes ship in the .NET framework itself. So that's what we'll talk about now. In the .NET framework, first, they have already defined, the .NET team has already defined for you a bunch of action delegates. There's 16 of them, or 17 of them, I think, something like that. There's an action that takes no parameters and returns void. All actions return void. It's kind of like saying a subroutine as opposed to a function. And then we have func down below. They all return not void. So anything other than void. So we have action. This one's not generic at all. It takes no parameters, returns void. We have an action that takes a type, one type, for its one argument, t1 arg1, and it returns void. We have another action delegate that takes 2 arguments, type 1 and type 2, and returns void, all the way up to an action that takes up to 16 arguments. And Microsoft said, if you need 17 arguments, you're crazy. You're just out of control. We're not going to support you if you need 17 arguments. 16 is as far as we go. So I don't think I've ever seen a method with more than 16 arguments, actually. It's pretty big. I'm sure they exist, but it can't be too common. OK, so those are the actions, and these are predefined. And because these are predefined and because they are generic, you should never have a need to define your own delegate type ever again. Now, there is one caveat to that, and that is, 2 caveats to that. If you need to define a delegate that has out or ref parameters, then you have to define it yourself. Or if you need to define a delegate that's constrained, where the generic type is constrained to something, then you have to define it yourself. And I'll be talking more about constraints later on in the slide deck, so I'll get to that more. After action, we have functions. They work exactly like actions, except they return a t result instead of void, a non-void value. So the first func is func that takes in one generic parameter, but this is the result, and it takes no arguments. We have another func that takes an argument, one argument, and returns one result. And then we have a func that takes 2 arguments and returns a result, all the way up to a func that takes 16 arguments and then returns a result back out. So again, because these are now predefined, you shouldn't have to define your own delegate types at all unless you need out or ref parameters or some special constraint on something. That's the only exceptions to the rule. And then, of course, collection classes and interfaces. And this is what we as software developers tend to use a lot in our code. So all the core collection classes, they now have generic versions of them where they didn't, non-generic versions existed in .NET 1. We have list of t, dictionary t key, t value, queue of t, stack of t. And a lot of these collection classes are based on interfaces. So there's some commonality between them, like IEnumerable, IEnumerator, ICollection, IList, all of t as well. And then, of course, the most efficient of all collection classes is array. Arrays are the most efficient in terms of their memory layout, also the most efficient in terms of accessing elements of the collection. You just index right into it and grab the element that you want. So on the base class of all arrays, there is a common base class, which is system.array, and I show it here. And they've added a bunch of methods to the array class, such as read-only, convert all, exists, find all, and so on. And all of these have generic versions. And this allows you to work with arrays or perform algorithms over arrays in a very efficient fashion, and in a compile time type safe way. So I picked just a couple of examples here, like the sort algorithm. So if you have a single dimension array of strings or a single dimension array of points, or a single dimension array of date times, and you want to sort them, you can call the static method on array called sort. You can pass in the data type, or you can try to let the compiler infer it for you, and then you can pass in some array, and then it will go and walk through the array and will sort all the elements for you. And then once they're all sorted, I picked another example here of binary search, which is another static method. And you can pass in the T or try to let the compiler infer it for you. And then you pass in the array and the element that you're looking for, and then it will scan the array using a binary search algorithm to try and find the element you want as quickly as possible. I give an example of this at the bottom of the slide where I create my byte array. I initialize it with a bunch of values. They're not in order. Then I call array.sort, and I pass in the array. Note that the type inference, I'm using it here, right? I don't have the angle bracket int32 there because the compiler's inferring it. And then I'm calling array binary search after they're sorted so that I can find where element 5 is, which will be in position 4 after they're all sorted. And again, I'm using the type inference here too in this method call. How are we doing on time? Okay. So I do have some demos, and I should probably show you one. I did mention the performance improvements that we get with generics. So all I mentioned it is one thing, but I can show it to you, and then you can see it. What I have in this example here is a variable count, and I've initialized it to 10 million. And then I wrote a little helper class here that just gets the time, runs some algorithm, gets the time at the end, and then it shows how long the algorithm took, right? It subtracts the end time, the start time from the end time, and it says this is how long it took. And what I'm going to do in here is I'm going to create a list of int32, and then I'm going to execute a for loop 10 million times. I'm going to add integers into the collection, and I'm going to pull the integers out of the collection, and then we're going to see how long that takes. Then I'm going to use the non-generic array list, which, as I said, the .NET framework still ships this with backward compatibility for people who are using it, because this shipped in .NET 1.0 and this shipped in .NET 2.0. And then we have a for loop here that will count again to a 10 million, and it will go and do the same adding, but in this case, the adding boxing is going to occur. So that means that there's going to be more memory pressure put on, and field copies are going to happen. And also, when you pull out, you have to insert the cast here. This is mandatory, or the code would not compile. And the runtime has to validate the cast. So there's a perf hit that happens here because of this. But you can see the two pieces of code are trying to accomplish the same thing. The only thing that's different is one's using a generic list algorithm, and the other one's using the non-generic array list algorithm. And then we're just going to run these, and we're going to see the time of the two. So we switch over here to my console window. I can make it a little wider. You can see that the generic algorithm did only 3 garbage collections because there was so little memory pressure that was happening, and it ran in 0.2 seconds or so. Whereas the non-generic one was substantially larger in terms of time, and substantially more garbage collections kicked in because of all the boxings that are happening on the heap. Now, you really see this in performance improvement when you're working with generics with over value types, and integer is a value type. But I have another example here that also shows performance. Again, I'm going to execute it 10 million times, and this time I'm using a list, but it's over a string. And string is a reference type, not a value type. And because it's a reference type, they're already on the managed heap, and so there is no boxing that's going to occur at all. Here I'm going to add the string x 10 million times to the collection, and then I'm going to go and pull it out, very similar to what I was doing a moment ago with the integers. And then I'm going to do the same exact thing with array list over here, where I'm adding in the x again, and then here I'm pulling it out. Once again, the cast is mandatory, and that does cause a little bit of a perf hit to happen. But the main difference here with this demo is that it's a generic over reference types as opposed to a generic over value types. And when I execute this, you'll see the performance difference between value types and reference types is dramatic. But you'll notice that the performance between the generic and the non-generic reference types is negligible. That's because we don't have all the boxing overhead. So there's not all these objects that are being allocated on the heap, and that's why the number of garbage collections is pretty much the same thing too. So in other words, using generics over value types tends to have significant performance and memory benefits to you. Using generics over reference types mostly gives you compile time type safety and not much else. Okay, it's not as significant a benefit as it is using generics over value types. Okay. That demo I'm going to skip. And now I'll go back to the slides, and we'll talk about generics infrastructure. To make generics work, as I said, I was on the .NET team at Microsoft for 8 years. I was there. And I started before .NET 1.0 shipped. And at the time when we were building .NET 1.0, we knew we wanted generics to be in the platform. But generics is an incredibly complicated technology to add. It really messes with the type system everywhere. As you can see, it has impact on classes, structures, interfaces, delegates, methods, and how all those things interoperate with one another. So when we started to work on generics in .NET, we knew it was a huge undertaking, and we wanted to do a really first-class job with it as well. We were also very late. When we were working on .NET, it always seemed like we were 2 months away from shipping. And then a year would go by, and people would say, when are you going to ship this thing? We'd say, we're 2 months away. We're just 2 months away, and then we will ship it. Then another year would go by. And we'd say, now it's 2 months, for sure. It's 2 months. So the pressure started to build, of course, during this time frame. And then eventually we said, we just can't get the generics thing sorted out. So we're going to let generics go, and we're going to ship it. So we did. We shipped .NET 1.0, and then we continued to work on generics. It was mostly done by a research team in Cambridge, England, that did most of the work there. And then we did a bunch of integration on the CLR team back at Microsoft's main office in Redmond, and which is where I was. So then we were getting ready to ship .NET 1.1. And we went to the Cambridge team in England and said, so we want to ship another version of .NET. Are you guys close? And they're like, no, we're not close. So we said, fine. So then we shipped .NET 1.1. And then when it was for .NET 2, we said, we need the generics now. And so we worked really hard to get generics in. And that was the main feature of .NET 2, was all the generic support. So you might ask, why was it so difficult to integrate generics into the platform? That's what we'll talk about now. So a lot of things had to happen. First, the Common Language Runtime is this virtual execution environment, and all the compilers for .NET, C#, VB, F#, and there's many others, many others. All those compilers, they go and produce this intermediate language bytecode that the Common Language Runtime then JIT compiles into native code to execute, what you want your program to do. Well, there's an IL instruction set that has things like, move here, move data from here to here, and add these things up, and so on. But there was no, there was an IL instruction called cast class, where you can cast to some data type. But there was no IL instruction to cast to a data type that was being determined at runtime, not at compile time. So they needed to add new IL instructions that supported generics. Well, once you add these new IL instructions, then you need a way to create data types that are generic. Like there was a way in metadata to say there's a type called array list or a type called even list. But there was no way in metadata to say there's a type called list of T. Right, or action of T1, T2, 3T, T3 all the way up to T16. So the metadata format had to be modified in order to support generics. Now, what produces this metadata and what produces these new IL instructions? Well, that's the compilers, of course. So all the compilers, the programming languages for .NET, had to be updated to come up with ways for you, developers, to go and specify what generic syntax should look like. So for the C# compiler, they said, well, we're going to use angle brackets, like angle bracket T, angle bracket. In VB, they decided they're going to use parenthesis of, and then a type, and then parenthesis. And every language had to come up with its own way of defining this. So there had to be new syntax that was created. The compilers have to support parsing that syntax. They have to spit out the new IL instructions and the new metadata. Well, if you have new IL instructions, not only do you have to find the IL spec, but you also have to modify the JIT compiler. And in .NET, we have an x86 JIT compiler. We have an x64 JIT compiler. We have ARM JIT compilers. Also in the time we had Itanium, IA64 JIT compilers. So all those jitters had to be modified in order to support these new instructions as well. And if you have new metadata and you have new IL, then at runtime, you can write programs that look at this stuff using reflection. So we needed to add new reflection APIs into the system that could say now, yes, there's a type called list. And is that a generic type? Oh, yes, it is. How many generic parameters does it have? Just one. What's it called? T. Or for dictionary, it has two. What are they called? T key and T value. So all these new reflection APIs had to be produced. And of course, they had to make them to be working. Then, of course, you want to modify the debugger. So the debugger shows you generics. If you're in a swap of T method and you're stepping through it in a debugger, wouldn't you like to know what the compiler thinks T was when it wrote this code? Was T a Boolean? Was T a stream? And so on. And then, of course, you wanted to modify or make IntelliSense work. So as you're typing, and you call, let's say, list add method, the IntelliSense comes up and says, add method requires a date time now because it's a list of date time. Or you want to say the add method requires a string now because you're trying to use a list of string. So it was a phenomenal amount of effort made by hundreds of people to really make this whole thing work, and this is why it took so long. So that you and I get to reap the benefits of the whole thing. All right, so now we're going to look a little bit deeper into the infrastructure. A class, a structure, an interface, or a delegate. Remember, there are 5 things that can be generic, and I just mentioned 4 of them. I did not mention methods. Okay, so I'm not including methods in this conversation. Only the 4 that are data types. With type parameters, that means a generic, one of these 4 things, is a type object in memory. In other words, the common language runtime will create an object in memory that represents the generic one of these things. And we call this an open type. Right? That's what we refer to it as. So there's an object in memory that represents type, a list of T. It represents list of T. And that type object, we call it an open type. And the runtime forbids you, it prevents you from creating any instances of an open type. In other words, you cannot new up a list of T. That won't compile. You can new up a list of string, you can new up a list of integer, you can new up a list of date time, but you cannot new up a list of T. The T has to be specified. And when you specify all of the type parameters for an object, you are creating another type object in memory, and we say that that is a closed type. And you can create instances of a closed type. Okay, so now I'll switch over and I'll demonstrate this to you to make sure that the concept is well understood. So here, I'm saying to the runtime, I would like to find the object in memory that represents the data type itself for dictionary, but not just dictionary, a generic dictionary. And not just a generic dictionary, but a generic dictionary that takes 2 arguments. Okay. So this comes back with a variable T that refers to this type object. Now, is this an open type or a closed type? User participation now. Open, correct, it's open. And now I'll do a console write line so we can see what the full name of the type is. So the full name of the type at the bottom here is system.collections.generic, that's the namespace it's in, .dictionary, backtick2. The backtick 2, the 2 is called the arity, A-R-I-T-Y, and this is how the runtime internally knows that this is a generic type that has 2 generic parameters. And what are those 2 generic parameters called? They are called t-key and t-value. That's what we are seeing over here. Now, I wrote a function here called new up a generic type, and I get to pass in a t. So this is using reflection here. I want to try to create an instance of this open type. Now, I'll step into this method to show you what it tries to do. I have a variable O of type object. I initialize it to null. No big deal there. And now I called activator create instance. This is a method that's been in .NET since version 1, and it's basically how you can say to .NET, here's a type referred to by a variable, and I would like to dynamically create an instance of this type. But as we just said, this is an open type. And so when I attempt to execute this line of code, it throws an argument exception. It fails to create it. And if you look at the message in the argument exception, it's a little cryptic, but it says, cannot create an instance of that type because type contains generic parameters is true. What that's trying to say is, this is an open type. Right? There's a really crappy way of saying that, but that's what it's trying to say. This is an open type, and I cannot create an instance of this open type. Okay. Now, on this next line of code, I'm saying type of, and I'm saying I want to use this type, dictionary string key. Now, I have defined this type. It's right up above here, dictionary string key. It is a generic type. It takes 1 generic parameter, t-value, but it's derived from another generic type, dictionary, but I've hard-coded string in for the key, but I'm passing the generic t-value down. And one, I wanted to show you this just to let you know this is doable, right? So it all fully works. Everything works great the way it's supposed to work. And it also shows that you can have generic types derived from generic types, and you can partially specify some of the generics. You don't have to fully specify. You can partially specify some of the types. That also works. You can see how complicated this whole thing is to make it work. So what I'm doing here is I'm saying I would like to find the object in memory that represents this dictionary string key type that is generic. Now, this variable t is going to refer to that type. Is it opened or closed? It's opened as well. And here I'll do a console write line so we can see it has the generics demo plus. By the way, all that means is that I defined that type nested inside my class here called generics demo. So it's the name of the class plus, and then the name of the other class that's nested inside of it. And then back here, okay. Okay, and then the backtick 1, the backtick again tells in metadata that this is a generic type. The 1 after the backtick says it's a generic type with 1 generic argument. What's it called? T-value. And then I can say, what is the base type? What is this derived from? Is it derived from an open type or a closed type? It's going to be an open type because we didn't say what t-value is. So this says it's a dictionary, backtick 2 is the base type, and I know the keys are strings, right? It knows the keys are strings, and the values, so I don't know yet. That's what makes it still an open type. And now I'm going to try to new up an instance of t. Will this succeed or fail? Correct, it fails. So the same argument exception as before, with the same error message as before, contains generic parameters is set to true, meaning that it's an open type. Okay, now in this example, I'm going to type of a dictionary, but look at this. I'm saying it's a generic dictionary, but now I'm saying explicitly in my source code that the key is a string and the value is a GUID. So is this t now going to refer to an open type or a closed type? Yeah, it's closed now, that's right. And one of the cool things is that The object for this type was generated at runtime on the fly, magically out of nowhere. Right? When the jitter jitted this method, it saw that this method referred to a type, a dictionary, string, GUID, and the jitter just dynamically created that type object at runtime for us because we called this method. It's really quite cool. Okay, so now if we do a console write line, we see that it is in fact a dictionary, generic with 2, so it's still a generic dictionary, but it knows for a fact that the key is a system.string and the value is a system.GUID. And as you all said, this is a closed type. So if I come into this method now and I call activator create instance, because this is a closed type, this is successful. And it does not throw an exception, and my variable O now refers to this an instance of this type that was dynamically created at runtime. This is insanely powerful. And now I can return the reference to this object back to my caller. And what I do here at the caller site is I take this pointer to some object that's in the heap, and then I say to the runtime, what is the type of this object that just got created? And it comes back and it says, it's exactly what you asked for. It's a dictionary where the keys are strings and the values are GUIDs. The thing you should be taking away from this discussion is that the type system is very rich. It's very rich and it is tightly integrated. So even though you're creating these things dynamically, reflection all works properly. I mean, everything was done to perfection here to give you a first-class experience when working with these generics. And understanding this can also answer questions for you. So here I will ask you a question that sometimes comes up in discussions I have at work. Let's say you have a generic type that has a static field in it. Okay, it has a static field defined in that type. Now, if let's say the type is called foo of t. So if I have a foo of integer, and then I have a foo of string, those two different closures over the open type, foo of t, if there's a static field in there, let's just say it's a static integer field in there, are those two closures sharing the same static integer, or does each closure get its own instance of the static field? So each closure gets its own instance, right? And if you understand everything that I just did here, then you understand that, right? Because each closure is its own separate closure. They're each going to get their own set of statics. So foo of string, it gets its static integer, and foo of whatever I said before, integer or whatever, gets its own static. And what if you wanted to have a static that was shared by all the closures? What do you think you might do then? Anybody want to scream an answer? Yeah, put it in a base class. I heard some people say it. Yeah, that's great. Put it in a non-generic base class, or at least a closed generic base class. Right? Put the static field there, then it would be shared by all closures up above. Right? So that's why it's really useful to understand all of this, because now you know how to write your code so that you can get the behavior you desire out of the code. Okay, a little bit more about infrastructure here. Here, also showing some more things about reflection. I have a variable t1 and another variable t2, both of the type. T1 is set to a date time, and T2 is set to a file stream. But that's only because I've hard-coded these in. But T1 and T2 at runtime could actually be initialized to point to any types. Right? I've hard-coded this in for the demo, but T1 and T2 could be set to types dynamically at runtime. Now I want to go and get the pointer to the open generic type dictionary that takes two generic parameters that are unspecified. But now I'm going to call this new method. And by new, I mean, since 2005. So it's new for generics, but it's been around for quite some time at this point. And then I can pass in here that I want to take this dictionary. At runtime, I'm doing this. This is dynamically happening at runtime. I want to create this new dictionary, and I want to create it where the keys are T1s, so the keys will be date times, and the values will be file streams. And this returned back to me this variable t. So does t refer to an open type or a closed type? Closed. And here, if we look at the string version of the type, we can see it's a dictionary where the keys are, in fact, date times, and the values are system IO file streams. And now if I call my method here, that's going to try to create an instance, because this is a closed type that I generated out of thin air at runtime, but it's closed, this does work, does not throw an exception. And so now I have created an instance of this type that I just created out of thin air at runtime. And I can return a pointer to this object back to the caller. And then the caller can say, hey, what is the type of this object that got created? And the runtime says, it's exactly what you wanted. Right? Again, showing how tightly integrated all this generic stuff is throughout the entire common language runtime. Okay, I am running a little bit out of time, so I think I'm going to skip the code sharing thing so I can get to the constraints. Okay, so now we come to a very important topic, and this also, a question that comes up very frequently is what's the difference between C++ templates, which have been around for decades now, and .NET generics? And the difference is dramatic. It's very dramatic. With C++ templates, they are written by a person who's writing code in C++, and they must be consumed by a person who's writing their code in C++. But because the common language runtime is a common language runtime, we want to make it so that people can write their generic algorithm in some language, let's say C#, and we want to let somebody using a different language, let's say Visual Basic, go and consume that algorithm. So what that means is you cannot do it by way of source code. Because if you wrote your algorithm in C# and your VB person wanted to use it, you would have to give them the C# source code. Well, the VB compiler can't compile C# source code. So in order to make generics work for a common language runtime, we need to be able to take your generic algorithm and we have to compile it to IL code without knowing what all the generic types are yet. And then somebody in a different language, like VB, they want to be able to consume that algorithm and specify the data types. But it had to have already been compiled. It couldn't be, the VB person can't compile the C# code. So this is very different from how C++ templates works. So let's take a look at what this means. In this example at the top, I have a method m, and it's generic, it takes a t. One argument of type t. And inside here, we have some simple code. I'm going to put the argument into a variable t, which is of type t. I'm going to take the argument, I'm going to call toString on it and put it into a string. I'm going to call the argument, take the argument and call a read method on it. Let's just say I pass some arguments here. And then I'm going to put it into n. When the compiler compiles this code, remember that it doesn't know what t is. In the generics world, right? In the C++ world, it would know what t is. But in the generics world, the compiler compiles this, and it does not know what t is. So the compiler says, well, can I create a variable t of type t? And can I assign something of type t into a variable of type t? Yes. That's all compile times type safe. It's guaranteed to work. And so the compiler says, that line of code is OK with me. On the next line of code, the compiler says, well, I don't know what t is. And you're calling a toString method that takes no arguments, and you think it returns a string. Is that true? And the answer is, of course it is true, because all types are derived from object. An object does define a toString method on it that takes no arguments and returns a string. And so it doesn't matter what t is here. For any and all possible t's, this line of code is good, and it will compile successfully. But then we get to the third line, arg.read. Well, there's many t's, types, for which there is no read method at all. Certainly it's true for system.object. There is no read method. And so because the compiler cannot guarantee that this will work, it will issue an error, and it will not compile the code. So you will get a compiler error, and this will not compile at all. So what can we take away from this? What we can take away from this is that when you are building a generic algorithm, it can only work if you are calling methods on object, because all types are derived from objects, or if you're doing simple things like assignment. But anything more complex than that, like read, will not compile. So if you think about that a little bit more, the next conclusion you'll come to is generics are practically useless. If that's all you can do with them, they are practically useless. So we were faced with this problem many years ago, and we said we want to add generics, but it turns out they're not that useful. So what can we do to make them be more useful? And so we came up with this idea with constraints. By adding this new constraint mechanism into the language and into the runtime, we can then bring more of the usefulness back to generics. So here's an example of a minimum method. The minimum method takes two arguments, arg1 and arg2. Now, the compiler knows they're both of the same type T, but the compiler doesn't know what type that is. Inside the method, we're trying to call arg1.compareTo. And normally, the compiler would say, well, there's lots of methods, or types rather, lots of types where there is no compareTo method. I can't guarantee that this code will work, so I will not compile the code. But with constraints, which is shown here with this where clause, that's your way of saying to the compiler, compiler, I know you don't know what type T is when you compile this code, but I will promise you something. Whatever type is specified for T, I promise you it implements the iComparable of T interface. So now the compiler says, oh, well, if you're going to make me this promise, then I know that interface does have a compareTo method on it. I know that compareTo method accepts a T. I see that arg2 is also of type T, so that works. I see the compareTo method returns an integer. You're trying to compare that with this 0 integer. Zeros can be compared with each other, so that's okay. And I see this method minimum is trying to return a T. I see I have a return statement here that returns arg1. It happens to be of type T, so that's okay. And if the if statement is false, then you return arg2, which is also of type T, so that's okay. And now the code compiles. Okay. So constraints reduces the number of types that I can use with this generic algorithm. System.object, for example, does not implement the iComparable of T interface, and so I cannot call minimum and pass in object for T. So I can't use all types. It's reduced the number of types I can use. However, for the smaller number of types I can use, I can now do much more with them. I can call compareTo, for example, and that makes generics much more useful again. Okay, there are three different kinds of constraints. There is a base class constraint, which you always have, no matter what. If you do not explicitly specify it, then object is assumed, right? That's what allowed me to call toString in the method m on the previous slide. But you can specify a base class constraint of a certain type, like stream. So I can say, well, here I'm writing a generic algorithm, and it only works for things derived from stream. That's a useful thing to do. We have three special generic base class constraints. You can put the literal class here, which means this is a generic algorithm that works on any reference type. You can put the literal struct there, which means this is a generic algorithm that works on any value type. And we also have a relatively new one called unmanaged, where you can say this is a generic algorithm that works on any blittable value type. This is typically used for interop scenarios to write a generic algorithm that talks to native code. So it's not used commonly by people, but it is a very nice thing to have. It's useful by more systems level programmers. I find it useful. There's the interface constraint, which is what I demonstrated on the previous slide, where I constrain T to an iComparable of T. And you can specify none of these, or you can specify many interfaces if you want to. And then the type being passed for T must implement all of the specified interfaces. And finally, the third kind of constraint is a new constraint, which you can either not specify at all or specify at most only one time. And it means that the type T must have a public parameterless constructor. And beware that there's a slight performance hit when using this, because underneath the covers it's calling activator create instance, so it's really being newed up dynamically at runtime. Also, there's an issue where that could end up resulting in a target invocation exception as opposed to an exception that you would normally expect. So it's a syntactical convenience, but it doesn't give you much of a runtime performance benefit. At the bottom of the slide, I give some examples of these. Here's a sorted collection of T, where the T is constrained to an I comparable of T. Here's a stream factory of T and P, where T is constrained with a base class constraint of stream. And also, the new constraint is being applied to T as well. So whatever type is passed for T, it must have a public parameterless constructor. I'm also constraining P here so that it's an I comparable of T. And now in the code here, I now get to call compare to on any variable of type T. Right? This constraint is now allowing me to call compare to on any variable of type T. And in this ... here, I can now call any method on stream on a variable of type T, or I can say new up the T paren. And for any variable of type P, I can call compare to on it as long as I pass it a T. And then I have some examples down here at the bottom where now the responsibility shifts to the consumer of the generic or reusable algorithm, where the person who wants to use the sorted collection, they pass in a type int32, and the compiler will now check, well, this int32 type, does it implement I comparable of int32? And if the answer is yes, and in this case the answer is yes, then the code will compile and everything's fine. On the other hand, if I try to create a sorted collection and let's just say I pass in some type foo, and it does not implement the I comparable of foo interface, then I will get a compiler error for the code that's trying to use the generic algorithm now. And if you read the error, the team spent a lot of time really working on these error messages to make them so that they're understandable. Now, because of constraints, your world gets flipped upside down, which is to say certain things you would expect to compile do not, and certain things you would expect not to compile actually do. And on this slide and the next slide, which I'll have to run through rather quickly, this gives an example of some of those things. So here I have a method foo that takes in a T, and here's where you would put the constraint, but currently it is unconstrained. I have no constraint in that location. So if I take some object, the compiler says, well, object is of type T, so I don't really know what type it is. And then I'm saying cast it to an int32. And the compiler says, no, I will not compile this code because I don't know for a fact that whatever type is passed here, let's say it's a string, for example, I don't know that that's castable to an int32. So the compiler will not compile the code at all. Now, I'm a little bit smarter than a compiler, and I know how to trick it. And you can trick it by taking the variable, casting it to object, and then casting it to int32. And if you do that, the compiler says, well, this is a T, and then I say, no, 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 it's an object. And it says, well, that's true, because everything's derived from object. And then I say, now cast it to an int32, and it says, well, okay. So that code does compile now, but at runtime, it will throw an invalid cast exception if, in fact, T is not an int32. So I've tricked the compiler into compiling it, but the runtime you cannot trick. The runtime always enforces type safety at runtime, and it will not be tricked. So if it sees you're doing something wrong here, the runtime will throw an invalid cast exception, and the next line of code will not execute. All right, on the next example here, I'm trying to new up a T. This normally would give a compiler error unless I put where T is struct. I can put that constraint up here. Because all structures or value types in .NET have a public implicit parameterless constructor on them. So this becomes legal. Or if I said where T : new, this means any reference type that has a public parameterless constructor or any value type. So this here is actually a superset of this over here. Now here I'm saying let's set T2 equal to null. Well, if T is a value type, this is meaningless, and so it does not compile. But if I say where T is a class, then I have said to the compiler, I promise you that T is a reference type. and therefore it is possible to set a variable of a reference type equal to null, and the code will now compile. Now, it's very useful. I know I'm out of time, but I'll finish up this slide in the next one, then we'll be done. I can do that, right? Iffy? Then I'm done. No, at least I'll do this one thought. So it's very useful to be able to create a variable of a generic type and set it to a default value. And this is what you would use for value types, and this is what you would use for reference types. But you would like to be able to set a variable to a default value without constraining it. And so they added this feature, if you will, to the language and to the runtime, where you can say default of t. And this says to the compiler, and you can do this without a constraint. That's the main feature, is you can do this without a constraint, because you would prefer to have fewer constraints as possible. It means your generic algorithm's usable by more types. So here I'm saying default of t, and if at compile time, JIT time, t is a reference type, then this becomes this. And if at runtime t is a value type, then this becomes this up above. And it's just determined at runtime. All right, I'll do the last slide really quick, and we'll be done. So here's another method foo. It takes two parameters, x and y. The compiler knows they're both the same type, but it doesn't know what that type is. Now here you're saying if x equals null, then do something. And here's an example where you think this should not compile, because if t is a value type, value types can never be equal to null. And so this code would never make sense in the case where it's a value type, and so it should not compile. However, the C# team thought about this, and they said, well, what are you trying to say here? What you're trying to say is, if the variable has no value, it's null, then go execute the code in braces. It just so happens that if x is a value type, it just always happens to have a value, and so this would always be false for a value type. So the compiler allows this to compile, and at JIT compilation time, when the jitter is producing native code for this method, it will see that the type of x is a value type, and it will actually optimize the whole thing away at runtime. That's very cool. Very cool that it does that kind of optimization. Removes the if statement, the jitter sees the if statement, and then any of the code in the braces would never be true, and so it optimizes the whole thing away for any version of this where t is a value type. It would optimize it away. But for t's or reference types, it would certainly keep it all in. The next thing here is equals, equals, and does not equals are operators, which is also similar to this operator plus over here. So we have this problem with generics, which is not a problem with C++ templates, but it is a problem with generics. And the problem is that the plus operator, it means add, right? But not always, actually, right? So it means add if x and y are integers. It means add if x and y are floating point values. It means concatenate if x and y are strings, though, right? So the meaning of plus is actually determined by the type of the operands. Same is true for equals, equals, and does not equals. The problem is that at compile time, if the compiler, all it knows is that x and y are of type t, it doesn't know the actual type. Therefore, the compiler doesn't know what plus actually means. Therefore, the compiler cannot compile this code. And this is our big Achilles heel with generics. This is our big problem that we have, is that a lot of people would like to create generic algorithms that do mathematical operations with using plus and minus and multiplication and division and so on. And you can't create those generic algorithms because the meaning of those operators is determined by the type of the operand, and we don't have it. And there's no way to constrain these today. I mean, you could conceptually add a constraint to some base class that has a static plus operator, but that's going to end up calling a method to do the plus operation, and none of the built-in numeric types in .NET overload this operator. It's all built into the compiler to do addition, subtraction, multiplication, and division. It's not built into the class library to do it. And so this is our big problem today. There have been a lot of attempts at trying to fix this problem, but none of them have been really good in terms of performance and efficiency just yet, but there are still people who are working on it. All right, and with that, I will end the talk. Hope you enjoyed the talk. Once again, I'll be outside to have more discussion, sign books, take pictures, and so on. And thank you for coming.